Good morning, ladies and gentlemen. On behalf of my co-author Jill Ross and myself, I would like to talk to you today about a study we undertook on the North Everest field. This is a gas condensate field under natural depletion, and like many similar fields, it produces a mixture of formation water and condensation water, which makes assessment of downhole scaling risks challenging. So in this presentation, I'll explain how we tackled this challenge and what the implications were for scale management on the field. I'll start the presentation by providing some background to the field and its scaling issues. Then I'll talk about how we evaluated the produced water analyses to identify the various formation waters present in the reservoirs, and how we estimated the produced formation water compositions and rates. Then I'll move on to describe the scale risk predictions undertaken, the results obtained, and how these results have been used to develop scale mitigation plans for the field, before finally I present our conclusions. The North Everest field is located in the central North Sea. It has previously been operated by BP and BG before it was acquired by Harbour Energy. Most of the production wells are platform wells, but there are two sets of subsea wells producing from the nearby accumulations of South Everest and the East Everest expansion. The wells considered in this study are either producing from the Forties formation or from the underlying Lister, Andrew and Maureen formations. This table shows the producing reservoirs for each of the production wells considered in this study. 4 were producing from the Forties formation and 4 from the Lister, Andrew, Maureen formations. Prior to acquisition of the field, some scale prediction studies had been undertaken, but these were not reliable because they did not use valid formation water compositions. There have also been several historical well interventions where calcium carbonate and barium sulfate scale has been identified downhole, and this has been removed mechanically. In the past, produced water solids have also been analysed via environmental scanning electron microscopy, and both inactive and active barium sulfate particles were identified, suggesting deposition of this scale in some wells. Since field acquisition, produced water solids have continued to be analysed occasionally, and inactive and active barium sulfate particles are still being identified. Scale has also been identified in surface facilities. For example, this photo shows a scale rim from pipe next to a liquid control valve. Unfortunately, a sample of the scale was not analysed, but we suspect it was barium sulfate scale. Barium sulfate solids have also been identified in the tilted plate separator. Prior to this study, and since acquisition of the field, there had been no scale events which caused loss of production. The only scale mitigation being undertaken at the start of this study was scale inhibitor injection at the ET04 wellhead. This was employed due to problems with the liquid control valve operation, which may have been scale related, and the produced water from ET04 was suspected as being a likely source. But it was evident that calcium carbonate and barium sulfate scale may be forming both downhole and in the surface facilities, but these scale risks were not well understood. As a result, a scale management review was instigated. The objectives were to firstly establish the current scale risks, and then to use this information to plan future mitigation and treatment requirements. To understand the current scale risks, a new scale risk prediction study was required, but this had its own challenges. To make the predictions, we needed to know the composition of formation water being produced from each well and the rates of production. But we only had produced water compositions and rates, and these were not representative of formation water compositions and rates because of the production of condensation water. Also, although a formation water sample had been collected from the Forties formation of an appraisal well and analysed many years earlier, the quality of the sample and the analyses was not known, and no formation water samples had been collected from the Lister, Andrew, Maureen formations. So the approach we took to estimate the formation water compositions and rates was to firstly use PVT modelling to estimate condensation water and formation water rates from the produced water rates. And then we estimated the formation water compositions from these results and the produced water analyses. The first task was to determine the chemical characteristics of formation water being produced from each well. This figure shows the produced water chloride and barium analyses for North Everest wells. The green symbols are samples collected from wells producing from the Forties formation, and the blue and red symbols are samples collected from wells producing from the Lister-Andrew-Maureen formation. You can see the analyses are grouped along 4 different slopes or lines of constant barium over chloride ratio. All the Forties data lie on one slope, and the Lister-Andrew-Maureen analyses are distributed amongst 3 additional slopes. Each slope represents a formation water with a unique composition. Actually, we found 5 different formation waters are being produced from the reservoirs, 3 from the Lister-Andrew-Maureen reservoir and 2 from the Forties reservoir. The location and occurrence of these different formation waters also provided useful information about the connectivity and plumbing of these reservoirs, and this is discussed further in the paper. For scale management purposes, we just needed to know which formation water was being produced from each well, and this evaluation of the produced water analyses provided that information. Although we now knew how many formation waters were present in the field, their compositional characteristics, and which wells were producing them, we did not know the actual formation water compositions, nor their rates of flow into the producing wells. To obtain this information, we undertook PVT calculations to calculate the condensation water rate for a large number of well tests when produced water samples were collected. For each test, we subtracted the condensation water rate from the measured produced water rate to provide an estimate of the formation water rate at the test separator. This then allowed the formation water chloride concentration to be estimated from the produced water chloride concentration using this equation. This table shows the calculated formation water composition for Forties formation water A, and you can see that the estimated chloride concentration is approximately 33,000 milligrams per litre. Perhaps more importantly, the uncertainty on this value is quite low, reflecting the consistency of results obtained from the many well tests conducted on wells producing this formation water. The remaining composition was then estimated using the estimated chloride concentration and iron ratios obtained from the produced water analyses. With this approach, we obtained good estimates of the compositions of 4 of the 5 produced formation waters, and they were consistent with analogue North Sea formation water compositions. Unfortunately, this approach was not successful for Lister-Andrew-Maureen formation water 1 being produced from ET14. This is because the water rates for this well were very low, and so there was significant uncertainty over the calculated formation water composition. So for this well, we had to use an alternative method to estimate the formation water composition, and again this is discussed further in the paper. Now we had the estimates of the formation water compositions and rates, we could undertake the scale risk predictions. Scale risks were predicted both downhole and at the wellhead, and also in the test separator under production conditions. We also evaluated the effect of uncertainties on the formation water compositions and rates, and looked at the effects of mixing of formation waters, but these factors did not significantly affect the results obtained. The calculations showed that there were only scaling risks from calcium carbonate and barium sulfate. We found that the scaling risks were dependent on the formation water rates for each well. For the low formation water rate wells, the scaling risks were higher downhole due to evaporation of the formation water as it entered the well. But higher up in the well, the scaling risks were significantly reduced due to cooling-induced condensation. For the higher formation water rate wells, they were less affected by evaporation and condensation, and the scaling risks were more a reflection of temperature changes during production. The calculations showed that there were low to mild calcium carbonate scaling risks under bottom hole conditions in 4 of the wells. Possible barium sulfate precipitation was predicted downhole for most wells, but in the case of ET14, precipitation was likely. At the wellheads and separator, there were no barium sulfate scaling risks for the low flow rate wells, but precipitation of barium sulfate was likely for the higher rate well ET04. But in all these cases, it's important to emphasise that the predicted precipitated masses were very low, so it was anticipated that the amount of deposition would not be operationally significant. When comparing the current predicted scale risks with current and past occurrence of scale at North Everest, there are many similarities which support the validity of our predictions. Firstly, the predicted types of downhole scale, that is barium sulfate and calcium carbonate, are consistent with previous occurrences of downhole scale at the field. Also, the presence of the scale rim near the liquid control valve may be explained by barium sulfate deposition from ETO4 produced water, as we suspected. Barium sulfate solids in the tilted plate separator vessel may have been transported from most wells after precipitation downhole and/or deposition from ETO4 produced water higher in the well or downstream of this. The predictions suggest that active barium sulfate scale may be being precipitated downhole in some wells and at the wellhead of ETO4, so this would explain the occurrence of this type of solid in the environmental scanning electron microscope samples. Also, the low filter coverage with barium sulfate scale is consistent with the low predicted precipitated masses. And finally, the mechanisms of barium sulfate precipitation identified from the simulations are likely to have been operating in the past, and so the inactive barium sulfate scale may have been derived from historic deposition via these mechanisms in the wells. Okay, so how have the results been beneficial to us? Well, firstly, the scale risk predictions highlighted that downhole barium sulfate mitigation would not be required. Given the historical records available at the time, this was an unexpected but pleasing result because it meant we could avoid the risks associated with the use of barium sulfate scale dissolvers. The main issue identified by the study was the potential for carbonate scale in the lower sections of the wells. After considering the potential historical scale deposition in the wells, we identified wells most likely to have significant scale build-up. This resulted in the shortlisting of 3 wells which would most benefit from intervention, giving us the lowest spend-reward ratio. Of these, 1 was selected for trial bull-headed dissolver treatment, and if successful, this will be applied to the other wells. The study also identified the risk of barium sulfate deposition near the wellhead of ETO4 and downstream of this, and so confirmed the requirement to continue scale inhibitor injection at the ETO4 wellhead to protect this well and the topsides facilities. By undertaking this review, there have been a number of benefits with respect to scale management on North Everest. Firstly, formation water compositions and rates for the field and the associated uncertainties are now fully understood. Factors influencing the produced water compositions and rates have been identified. And because of this, and because we have cleaned up the produced water analyses database, our ability to quality control produced water samples and analyses has improved. Now that we understand the composition of the formation water being produced from each well and the rates, we are now in a position where it's possible to determine ongoing scale risks to each well. The work has allowed us to target and prioritise particular wells for scale mitigation treatments. And we have also ensured that unnecessary scale mitigation treatment and associated risks have been avoided. And finally, by adopting the approach and methods used in this study, we expect our treatment success rate to be increased and the risk of a poor spend-reward ratio to be reduced. Okay, and to conclude, a scale management review has been undertaken on the North Everest field. This has been aided by our evaluation of available produced water analyses and associated PVT modelling, which has generated formation water compositions and rates for each well, and by scale risk predictions and their comparison with current and historic scale observations. The study has demonstrated that the current primary risk to North Everest wells is downhole calcium carbonate deposition in some wells and not barium sulfate precipitation, as was previously thought. And finally, the review has allowed only those wells requiring treatment to be targeted, and their treatment to be prioritised and tested, hence reducing risks and the spend-reward ratio. We would like to acknowledge Oilfield Water Services Limited and Harbour Energy plc for their permission to publish this paper. And we would also like to thank Harbour Energy onshore personnel, Siv Yayakumar, Remy de Winter, David Brands and Simon Barons for their assistance with this study. and also Champion X personnel for their help, that is Rebecca Ritchie, Claire Johnson and Miles Jordan. And finally, we'd like to thank Tekna for organising this conference under challenging circumstances and for selecting our paper for presentation. And with that, I'd like to thank you for your attention, and we'll be pleased to answer any questions you may have about our work. Thank you.